Okay, what I want to talk about now is ways to take the inverse transform. The textbook is a little bit um, incomplete on some of the ways to take the inverse transform, especially on partial fraction expansions. So I'm just going to go over a little bit about how to do that. So first of all, let me get everything where we can sort of see most of the stuff at the same time. Here we go. So first of all, to take the inverse transform, particularly if you're going to use partial fraction expansion, it is important that you have a rational function, one that contains a polynomial in the numerator and a polynomial in the denominator. And the other thing is, partial fractions only work if the order of the polynomial in the denominator is higher than the order of the polynomial in the numerator. So if you don't have that situation, you have to use long division so that you can get the order of the numerator lower than the order of the denominator. The other thing is you want your denominator polynomial, you want the highest order term to have a coefficient of 1. So typically you would want to divide out this b sub m so that this s sub m has a denominator of a constant of 1. So the first step is you want to factor the denominator. Now, if you have a higher order denominator, you want to use MATLAB or some other computational tool to do your factoring. Higher order than, say, second order. But a lot of times, for a lot of reasons, we have the function already factored. So step 2 depends on your denominator roots. So here's an example of a problem that's already been factored. And we want to use partial fraction expansion to take the inverse transform, because taking the inverse transform is always done by looking at the table. So we want to get our functional form to be equivalent of that in the table. So what that means is each of the factors in the denominator we want to form a single term. So partial fraction expansion is like finding a common denominator in reverse. Instead of finding a common denominator between these three terms, we're saying, well, we already had the common denominator because we have this denominator and these are individual factors. There must exist some sum of terms that would give us this equivalent expression. So we just create three unknowns, a, b, and c, and enter each of those as a numerator term. And then what you want to do is find a common denominator on the right-hand side. And when you do that, you can then have the same denominator on the left-hand side and the right-hand side, and you set the numerators equal to one another. So this line here basically shows that. This is the numerator on the left-hand side. And then on the right-hand side, if we were to find a common denominator, this would be the numerator on the right-hand side. And now you have one equation with three unknowns, but this equation must hold true for all values and any values of s. So the trick is to choose convenient values of s that will make some of the constants go to 0 and make the other constants easy to solve for. So the first thing we want to do is we want to choose s equals 0. That'll make the third and second term go to 0, and only the first term in this expression is non-zero. So out of that we'll get 48a is equal to this expression. So the 48a comes from the right-hand side of this equation. And this expression comes from what happens when you plug in s equals 0 to the left-hand side. And so we'll continue. A couple of other obvious options are to choose -6, which would make your first two terms go to 0. -8 will make your first and third term go to 0. So doing that, respectively, we're able to solve for a, b, and c. And then you simply take your solutions for a, b, and c and plug in to your partial fraction expansion. And obviously it's important that you do them in the right place. So, the 120 has to go over the s and so on. And now it's relatively easy to take the inverse transform term by term. because at this point we have each term representing something that is easily found in the table. So real roots in the denominator of an expression in S result in constants, so either constants or decaying exponential. So if your root is equal to 0, then you get this 120 u of t, which is basically a constant. If your root's equal to a real number, then you'll get a time decaying exponential. So you've got these two terms. And this is true for any order. So if we had a fifth order polynomial and all the roots were real, we would get 5 time constants. In the physical world, usually one of those dominates over the others. Usually the slowest one is the one that you're most concerned about. So that's what happens if you get real roots. Now, sometimes you'll have real repeated roots. So this is an example. This term in the denominator, s plus 5 cubed, is an example where you have a triple root at -5. And then you have another root at 0. Now remember, we have to ask ourselves, what is the most general form of individual factors that, when we find a common denominator, could give us this final expression? And so the answer is we would obviously have something over s, and then we could have a factor that was s plus 5 cubed. We could also have a factor that was s plus 5 squared, and we could also have a factor that was s plus 5. So remember, what we're really doing is representing a differential equation with this. So if you have a fourth order polynomial in the denominator, that means you had a fourth order differential equation, which means you will generate 4 constants of integration. So in our partial factor terms, we will have 4 unknown factors, 3 associated with this third order root. They don't all have to be non-zero, but in the most general case, we have to consider that they're there. So same thing, finding a common denominator and setting the numerators equal. So we're skipping that step where we would show this as a rational function, and we're just saying the denominator is the same on both sides, and here's what the result will look like. Now there are 2 choices here for how to solve. One is you can basically expand the right-hand side, and you'll have terms in s cubed, terms in s squared, terms in s, and terms that are constants. And then you use the trick that says if I have a polynomial on the left-hand side and a polynomial on the right-hand side, the coefficients of the same order terms have to be equal. So for example, on the left-hand side, I have 100 multiplying s. On the right-hand side, I'll pick up an s term here, and here I have b, and then I'll pick up a 5cs, and over here I'll pick up an s term from the cross term. So I'll take all of my, I'll collect like terms, and everything that multiplies an s on the right-hand side will be equal to 100 on the left-hand side. So that's one option. The other option is to just select 4 different values of s and solve for simultaneous equations. You can see, obviously, s equals -5 is an obvious choice. When we had different roots, we could just pick the roots, and that made it very simple. In this case, we have a triple root, so we can only use 5 once, so we'll have to come up with 2 other choices. So for method 2, I chose a equals 20, and I'm sorry, I chose s equals 0 and s equals -5, which solve for a and b fairly easily. So I come into my equation and I substitute for a and b, and then at this point I just pick something fairly easy. It's going to give me small numbers when I square them. So I picked -4 and -3, and when you do that, you'll get 2 equations and 2 unknowns, and you'll find that a is 20 and b is -400. You'll get this equation, c plus d is -120. You'll get another equation, c minus d is -80, so you can solve for c, which is -100, and d, which is -20. So plugging in, we have a numerator now for each of these terms. Turns out none of them were 0. So from the first term, we get u of t. From the last term, we get a time-shifted u of t. And then remember that we can look up in the table and see that when we have this 1 over s plus 5 squared, that brings up a t in our solution, and 1 over s cubed terms correspond to a 1/2 t squared. So how do we get that 1 over s cubed? Well, 1 over s cubed is basically 1 over s times the transform inverse times 1 over s squared. And so remember that 1 over s in the Laplace domain corresponds to integration in the time domain. So basically, if I have a t term, that's going to integrate to 1/2 t squared. So this 1 over s plus 5 cubed then gives me 1/2 t squared e to the minus 5t. So each additional power down here will bring up another multiplication by t. So if it's 1 over s plus 5 squared, it brings up a t. If it's 1 over s plus 5 cubed, it brings up 1/2 t squared, and so on. And you can find that in the table. Actually, those are fairly common formulas. So my result is I have a u of t, I have an exponential decay, I have exponential decay multiplied by t, and I have exponential decay multiplied by t squared. Now, if you recall from the first part of the course, we talked about the modification rule when we had higher order derivatives with multiple roots when we found the characteristic equation. So remember what happened then is we had a possible term that was e to the minus as, which is what we've generated here. But then for each order of root, we generated a multiplication by t. So the second order, if it were a second order root at a, we would generate t e to the minus 5t. If it were a third order, a t squared e to the minus 5t. So we talked a little bit about that when we talked about higher order differential equations. Now method 2 is the method of equating coefficients. This is very similar to when we did the power series method in differential equations, and we equated coefficients in order to generate an expression that would give us a series solution. So what you do here is I've got my little binomial expansion coefficient table here. You basically calculate s plus 5 cubed and substitute in term by term. Same with s plus 5 and your s plus 5 squared. So this is just mathematically just multiplying everything out. And then what I want to do is collect like terms. So I look at my s cubed terms. I have 0 on the left hand side. On the right hand side I have a and d. So a plus d is 0. Then I collect my s squared term. I generate this equation. My s term, I generate this equation. So these are the coefficients of the left-hand side expression and the right-hand side expression respectively. So from that you can see a is pretty easy to solve for, which then generates d from our first equation. And then plugging in values of a and d into equations 2 and 3, I can get 2 equations and 2 unknowns, and I get the same result as what I had before. So talking just really briefly about polynomials in general. Polynomials have 3 types of roots. So if you have a quadratic, your options are you have 2 real distinct roots, you have a repeated root, or you have a complex conjugate pair. Now as you go higher order than quadratic, all higher order equations are combinations of a quadratic and a single order. So if you have an even order polynomial, that factors into quadratics. And then each of those quadratics can have these possible roots. If you have an odd order polynomial, that's going to factor into one real root plus quadratics, which could have any of these 3 options. So in general, your quadratic might look something like this. If you wanted to have a perfect square, then your middle term is basically twice the square root of your constant term. So if you have 2 real roots, you sort of determine whether your roots are real or imaginary or double root by looking at the outcome of the quadratic formula and whether it's real or imaginary. So as an example, if I have s squared plus 6s plus 8, just thinking in my head, b squared minus 4ac would be 36 minus 4 times 8, which would be 4 times 8 is 32. So because that's a positive number, the roots are real. I can also do that by kind of evaluating the relationship between these two coefficients, which is summarized here. If you take 1/2 of the middle term and square it, if that ends up being less than the constant, then the roots are complex. In our case, that ends up being greater than the constant, telling us the roots are real. So here's another example. In this case, if we take the 7 and we take half of it, that's 3.5. If we then square that, we get 12.25. That's greater than 12. That's going to tell us we're going to have 2 real roots. Or you can do the b squared minus 4ac thing. So we find the roots, and we get the roots are minus 3 and minus 4. Then it's important to know that when you plug back in for f, it's s minus a negative 3 and s minus a negative 4. And this becomes important if you use something like MATLAB to do your partial fraction expansion. Because MATLAB will do a partial fraction expansion, but when it gives you the roots, it gives you the roots in this form, and you have to then go back and plug them into the expression. So once I have that, I can put that back into my expression, and then I can do my partial fraction expansion and solve for a and b, giving me a result. Okay, in this case, I have an expression that is not going to yield real roots. It's going to yield complex conjugate pairs. When you get complex conjugate pairs and you're trying to take the inverse transform, remember the whole goal here is to match what we find on the tables. And so if you want to effectively match what you find on the tables term by term, you need to complete the square in the denominator. So we take this expression and we figure out, what do I need to make a perfect square, given that I have a 6s as my middle term. And so what I need, just depending, and there's a number of ways, most people can do it in their head and know that what I need here is a 9. What I have is a 25. So a couple ways to think about it. One way is you add 9 and you subtract 9 so that you've effectively added 0. And then you can group these first 3 terms into a perfect square and this second term into another constant. And so I can then express that as s plus 3 quantity squared plus 4 squared, which if I write it down, it looks like this. That's very similar, if I look up in the table, that's very similar to the expression for e to the minus 3t sine of 4t. The only difference is I really need a 4 in the numerator. So I multiply by 4 and then I multiply by 1/4. I pull the 1/4 out. So when I take the inverse transform, then this 4 over s plus 3 plus 4 quantity squared, or s plus 3 quantity squared plus 4 squared, that inverse transforms directly into e to the minus 3t sine of 4t, and my 1/4 comes out as a constant. Here's another example where I have that same kind of denominator, but I also have this s term. So now I need to express that as something over s and something over that denominator. If you have a quadratic that will not factor, when you do your partial fraction expansion, you have to have a bs plus c in the numerator. The reason for that is because you're not going to factor this. Once again, you're trying to figure out, the maximum number of way, or the way to unravel this completed expression. So in general, you could have an s term in the numerator. So using the method of equating coefficients, I come up with a equals 5, b equals minus 5, and c equals minus 30. So plugging those in, I'm going to get 5 over s and then plus minus 5s minus 30 over my quadratic denominator. Factoring out the minus 5 so that I have this in a more easy to view form. And now it's time to complete the square. So this is what I end up with. So remember in the table, when I have this expression in the denominator, in the numerator, I either want an s plus 3 or I want a 4. Since I have an s, that tells me automatically I'm going to have a sine term, so I'm going to take this term in the numerator and I'm going to split it into one term that'll inverse transform into sine, and into another term that's a constant only. So then split that out into two parts, and notice I still have my -5 coefficient here. Now this term is going to inverse transform as the cosine. This term is very close to inverse transforming as the sine. What I want is a 4 in the numerator, so I get that by multiplying by 4/3, then multiplying by 3/4. So my 4/3 times 3 is going to give me my 4. My 3/4 is going to come out as a constant. So this will give me 15/4. This is going to transform into sine. This is going to transform, inverse transform into cosine. So the final expression is as follows. Remembering that really each term is multiplied by a u of t. There is another way to do that. You can actually break that up into complex terms and complex roots, but most of those are not given in the table, so it's highly advised to try to complete the square. All right, I want to skip on down. Well, here's an example where I have an s term and then I have an s squared plus 4 term. So this is another case where this s squared plus 4 can't be factored into real roots. So you have to, when you do your partial fraction expansion, you have to do that as bs plus c in the numerator, because this has a square. And so solving for a, b, and c, you get c is 1, a is 1/2, and b is -1/2, so you plug that in. And now this first term obviously is going to transform to the inverse transform to exponential decay. But this second term, this s squared plus 4, inverse transforms into some combination of sine and cosine. So what I want to do is I want to separate out the term that's got the s and the term that's got the 1. So I just take this and split it into 2. And then I work with each one separately in order to get the right combination, so I get the numerator constant correct. So in this one I factor out a 1/2. In this one I break this one up into 2 times 1/2 and factor out a 1/2. And so then my result is I have the cosine expression and the sine expression each multiplied by a constant. The final thing to talk about in partial fraction expansion is what do we do if the denominator is bigger, or if the numerator is of higher order than the denominator. Bigger is probably not a great descriptive term. These are my personal notes, so sometimes I write silly things. So in this expression I have an s cubed over a denominator that's second order, and I can't do a partial fraction expansion on that. So what I have to do is I have to do long division. So in long division you do it just like you do long division of numbers. You write your numerator under the division sign, and then you write your denominator over here. And just like in actual real numbers, we're going to look at the highest order term. That's analogous to looking at the highest digit. We're going to look at the highest order term here, and s squared will go into s cubed s times. And then you're going to take your s and you're going to multiply it by this entire expression. So that's where this line comes from, s cubed, 5s squared, and 6s. And then just like in long division, you're going to subtract that. So s cubed minus s cubed is 0. I bring down negative of these two terms. Now s squared will go into -5s squared minus 5 times. So I repeat the process, and what's left over is 19s plus 30. Now this is of lower order than my denominator, and so this is considered a remainder. So I can now write the expression s minus 5 plus my remainder over the original denominator, which can be factored into s plus 2 and s plus 3. So my partial fraction expansion will look like a over s plus 2 plus b over s plus 3. I ignore this part and do a partial fraction expansion only on this part, giving me an a of -8 and a b of -27. So you can see when you substitute -8 here and you take the inverse transform, that's going to be exponential decay. Same here, it's going to be exponential decay. The inverse transform of 5 will be the impulse function, and the inverse transform of s is the first derivative of the impulse function. How do I know that? Because I'm applying the derivative property that says multiplication by s in the Laplace domain is differentiation in the time domain. So that concludes the lecture on the inverse transforms. You have a hard copy of these notes, and so you're welcome to use them as you wish, and view the video if it's helpful.